You see it everywhere. It's the most common man-made material on the entire planet, literally the foundation of our modern world. But what if I told you that concrete has a secret, a kind of hidden flaw that can cause it to slowly and silently tear itself apart from the inside out? Yeah, so today let's dive into this hidden chemical betrayal. So you've probably seen this, right? These sprawling, kind of map-like cracks on a sidewalk or a big dam. And you probably just thought, it's just normal wear and tear. But here's the thing. This isn't damage from the outside in. This is concrete basically self-destructing, and the problem starts deep down inside the material itself. So the big question is, what's causing it? All right, to get to the bottom of this, we have to start by tearing down a huge assumption, something engineers believed for decades about what concrete is actually made of. For the longest time, everybody just assumed that the aggregates, the stones and sand you mix into cement, were just inert fillers. They were just kind of there to take up space, add some bulk, but they didn't really do anything chemically. But the reality? Well, science has shown us that some types of aggregates are anything but inert. They can be chemically reactive, and they can become a star player in a really destructive reaction. Okay, so if some of these rocks and sands are active suspects, what exactly is the chemical crime they're committing? Let's take a closer look at this whole treacherous reaction. It's officially called the Alkali Aggregate reaction, or AAR for short. And like the name suggests, it's a reaction between two main players. You've got the alkali metals, stuff like sodium and potassium, which are just kind of hanging out as impurities in cement. And then you have certain reactive minerals, like some forms of silica that you can find in some aggregates. But here's the kicker. Just having those two things isn't quite enough. For this disaster to really kick off, you need a trio. It's like a recipe for destruction. You need the alkalis from the cement, you need the reactive minerals in the aggregate, and you need water. When all three of those things get together inside the concrete, well, the stage is set. So, how does this combination of ingredients lead to the massive cracks we see on the surface? Let's break down the exact mechanism, the play-by-play of how this stuff causes huge structures to crack. It all unfolds in four main steps. First, the alkalis and the reactive minerals get together and form this weird gel-like goo around the aggregate particles. Second, this gel is incredibly thirsty. It's like a little sponge, and it just starts sucking up any water it can find from the concrete or the environment. Third, and this is the critical part, as that gel soaks up all that water, it swells up, it expands, and this expansion creates this immense pressure inside the concrete. And finally, that pressure just builds and builds until the concrete can't take it anymore, and it cracks from the inside out. Now, you have to understand, this is not a fast process at all. It's a super slow burn. It follows this classic S-curve life cycle. There's usually an initial period, for months, where nothing much seems to happen. Then, over a period of years, it hits a rapid expansion phase. Now, the good news, I guess, for engineers, is that it doesn't just go on forever. After a few decades, the reaction slows way down and eventually stops as it just runs out of fuel. But the damage it leaves behind? Oh, it's severe. You get that widespread mat cracking we saw at the beginning. The concrete loses its strength, its elasticity, and with all those new cracks, its durability and ability to keep water out are totally compromised, which lets other bad stuff get in. It even puts extra strain on the rebar inside. And let's be honest, it's just plain ugly. So if this is such a slow-moving but really destructive problem, how can engineers get ahead of it? Well, this is where the forensic work comes in, testing the materials before they ever become part of a building or a bridge. There are basically two main tests they use to screen the aggregates. You've got the quick chemical test, which is fast. You get results in about 24 hours. They basically grind up the aggregate and throw it in a strong alkali solution to speed up any reaction. It's great for a first look. Then there's the mortar bar test. This one is way slower. It takes months, but it's much more realistic about what's actually going to happen in the concrete. They make little bars with the aggregate and just watch them for any expansion over time. All right, so knowing the problem and how to spot it is one thing, but how do we actually prevent it? How do we build better, more resilient concrete? So for new stuff, the whole strategy is about prevention. The best option is super simple. Just use aggregates that you've tested and you know are non-reactive. Easy. If you can't do that, you can go after the other ingredients. Use cement that's low in alkalis, or add other materials like fly ash that can help stop the reaction. Now, for buildings that are already having this problem, the options are way more limited. The reaction's already happening, so the main goal is just to starve it of that third ingredient, water. Slapping on surface coatings can help block moisture from getting in and fueling more expansion. Now hold on, because here's a totally fascinating and counterintuitive twist. You might think that if you have to use some of that reactive aggregate, diluting it with some good non-reactive stuff would be a smart move, right? A good compromise. But in some cases, that can actually make things worse. A lot worse. This is what's known as the pessimum paradox. And it's a real head scratcher. Check this out. Using 100% reactive aggregate causes a lot of expansion, sure, but look at that middle bar. A specific mix, the pessimum mix, causes the maximum possible damage. Why? Well, the theory is that with fewer reactive particles to go around, all the alkali in the cement becomes more concentrated on each one, basically supercharging that destructive gel formation. It's wild. So really, the crucial point here is that something that seems so simple, like concrete, is actually an incredibly complex chemical system. And understanding that chemistry, from the reactions in the mix all the way down to the minerals in the rocks, is absolutely essential if we want to engineer structures that are safe, durable, and built to last for generations. It really makes you wonder, doesn't it? If the very ground beneath our feet, the stuff we build our entire civilization with, has these kinds of hidden complexities, what else in our everyday world isn't quite as simple as it appears on the surface?